Can you hear me?
Yes.
Awesome. Nice to meet you.
So have you clicked the button like start the session? Because
Yeah.
I guess so we are live right now. Okay.
Yes. Right?
Yeah. Hmm.
Okay. Okay. Good. I think I'm ready.
Cool. Maybe we can like wait 1 minute and then just start away.
Sure. Of course. How's it going?
Cool, cool. How about you?
Good. Good. Looking forward to it.
And also, how do you like the questions at the end
Um,
after the
we,
presentation?
yeah, we can just take them from people, or if they have them in the chat, I think it will be helpful if you let me know. So I think so we
Hmm.
don't miss questions. I will be checking the chat as well, but in case, could be good.
Okay.
Will that work?
Yeah, yeah, yeah. Of course. Okay, so we can start. Floor is yours, Clora.
Okay, well, thank you very much. Welcome. Thank you for taking the time to join us this afternoon. Um, I'm Claudia Molina. I will be talking to you about leveraging AI to enhance subsurface evaluation capabilities in oil and gas. I am the president of Segwin Technologies. We specialize in applying advanced technologies to existing oil and gas workflows and also using AI to enhance productivity and evaluations that are very traditional for oil and gas, especially in unconventional reservoirs. So, we are going to start. We're going to give you just an introduction on who we are. We're going to give you a high level overview of the oil and gas industry and some priority trends that we're seeing for this year. I'm going to share with you two case studies where these advanced techniques have helped enhance the workflows that are traditionally used for subsurface evaluations, and that includes data science techniques to enhance physics-based modeling and, of course, the efficient identification of well workover opportunities through the use of machine learning. We're going to have some key takeaways from this, and I will be taking questions. First, I want to share a bit more with you about why I'm passionate about this topic. I have spent in the oil and gas industry about 23 years across the value chain of the upstream sector of oil and gas, including asset management, reservoir engineering, production engineering, uh, data science, business development, and completions engineering. I have worked on across the U.S. on some of the most prolific basins, onshore U.S. and also international. I have managed quite a few properties, oil and gas properties, and have worked on business development transactions. My formal training includes engineering degree and also a couple of masters, one in data science and another one in it's really important to me to actually blend these concepts, engineering, data science, and business, to be able to deliver value. And that's really where I have focused in my experience working for these operators or other operators on top of this too. But these are some of the operators I have worked with. I have also been involved with the Harvard Innovation Lab, which has been really helpful to understand what tools and techniques have been used or are being used and deployed in other industries outside the oil and gas industry. I have been doing that for a few years, and it's been really helpful to understand how this is being applied by other startups. For example, concepts of data science and machine learning are being applied in healthcare and fin in slightly different ways, some more advanced in some levels to what we are traditionally using sometimes. So it's really interesting to me to bring that learning or those learnings to what I do and what I know most, which is oil and gas. That's why I worked on forming Segwin technology. Segwin, we are focused on delivering just that, the engineering, business, and technology, and also upskill programs to oil and gas, um, focusing on process automation and digital product development, utilizing the expertise in oil and gas and also these advanced techniques, advisory support, of course, within the oil and gas segments, especially upstream oil and gas, and upskilling. I'm not doing that on my own. I have some partners which are very helpful in helping deploy the solutions across the different customers. So I'm going to share with you some of the oil and gas industry trends that we're seeing this year. And oil and gas, we're embracing sustainability. We're really driving digital transformation and automation. The adoption of these technologies is taking off quite significant. We are adapting to geopolitical and supply chain dynamics, and we're focusing on emissions reduction and ESG. We're also trying to realize value from the deployments of capital and investment and technology development that we have done in prior years. All of this involves a lot of data. So that's really an exciting time for oil and gas because we are trying to drive all these uh, trends all with the common denominator of data. So it's a really priority to start leveraging data infrastructure, data management systems, and better utilization of our existing data. So for oil and gas, we have quite a few sources of data. We have many disciplines to help us understand how we're gonna deliver more value. And of course, if you look at the right here, I'll share with you here. This is visualization provided by McKinsey, which I think is really, really interesting because it summarizes and highlights the different final elements for processes and systems when it comes to data. And it also helps understand what can happen if some of these processes and systems don't really get managed properly or are broken. For example, in data capture, of course, if we don't do an effective data capture program, or integrity is not going to be well maintained. In infrastructure setting, well, we're not going to have effective stored data effectively stored and utilized, and so on and so forth. I like it that it includes people and skills because even if we have all of these segments here really well taken care of, if we don't really elevate the subject matter expertise, the data will not necessarily be used in decision making, which in turn degrades value, right? As I was mentioning, for oil and gas, we have several different types of data and sources of data. So it really becomes a challenge to try to get them in a holistic place to be used appropriately. It's a big effort trying to get all these data systems that are somewhat different vintages, different resolutions, different magnitudes to a place where they all can be applied in one single workflow. This is, for example, just a quick snippet of how the different data resources or sources that we have in engineering world, which can be anywhere from internal to the company to external to government to different science and technology applications that we do to our wells, to environmental records. So different industry standards across regulatory bodies, it can be very messy at times. And of course, that brings quality considerations, right? Completeness, timeless, accuracy. With all in all that said, these are some of the challenges that we have, but the first priority, as has been noted by many people, is process automation for a lot of small to medium enterprises in oil and gas. So to give you an idea, so just as a holistic way, these are some of the workflows that we traditionally use to unlock more value from subsurface evaluations. We have the traditional diagnostics from our production data, which it requires certain amount of data. Analytics, which is more useful and more fundamental, using more fundamental principles of fluid flow. We of course have statistics and machine learning, and all the statistics-based approaches, which require a significant amount of data, and it's useful for predicting observed behaviors. But we also have on the other side a more detailed view of our well or reservoir performance. For example, in what we call 3D modeling, or numerical modeling approach. That solves a system of partial differential equations that describe the physical properties of fluid flow. It can be an iterative, fit-for-purpose process that can be very time-consuming and is very localized sometimes to the area. So, in a sense, some of these workflows provide a high-level view of all the data that you have available, or some of the data, and some of the other workflows provide a more detailed view at the well level. So the idea is to extract value from all these workflows in a cohesive. Each view will get you a more holistic view of the picture of the reservoir you're trying to describe. So, in a sense, we know that not every workflow has the same value or brings the same value to the table. Workflow complexity doesn't necessarily reflect in value. You can have a very complex workflow, but it might not necessarily give you more value than a more simplistic workflow. And the idea is to couple the right workflow at the right resolution to get high confidence predictions of the production of oil and gas at the regional, localized, and well level predictions, just like we saw before. So, to do that, it takes a heavy amount of expertise and data to be able to understand the system at a regional level, localized level, and then well by well predictions. So, the first case study that I'm going to share is just going to help understand how to couple these technologies to get both sense the high level vision and also the more detailed well level resolution to add value. This specific case, it was for this operator had a lot of different wells in a tight gas setting. They were late life field wells, which means they were in the decline, a really low decline rate, and really low producing wells. There were a significant number of them. Normally, when you have this many wells that are producing at low rates, there is a bit of a reactive approach to production remediation. Wells will go down, and then the team will react to go fix it, whether or not after a time has passed and they have had the chance to do the evaluation. The diverse data sources are still there, kind of like what we have discussed. The challenge was to provide an efficient identification of production uplift opportunities. The idea is then, if you have that many number of wells, the detailed high-level resolution workflows that I described earlier, it's really difficult to apply those to every single well and predict, for example, when a well is going to go down. That's where the high-level resolution work comes in place. For example, applying machine learning for the rapid screening of uplift opportunities provides a significant advantage to be able to hone in instead of looking at 1,000 wells at a detailed level. You can actually high grade which are the wells that are more likely to add value or more likely to require remediation. So the idea is to couple this, the machine learning workflow for rapid screening of opportunities, and then apply the detailed level engineering evaluations to really validate that subset of data and deploy the appropriate treatment. So that's what was done in this particular case. And through that, we went and actually recognized that there were about 56 production uplift opportunities from the initial, 1,000 wells or so. And with that, the initial field trials show some positive results from the 56 uplift opportunities that were strategically selected. This was also helpful because it minimized the amount of resources that were needed to be deployed in this field. Normally, these large fields are going to have significant amount of wells, and you can deploy your talent or your people to work on wells that have higher value right off the bat instead of having to sift through every single opportunity. Second case I want to share with you is a bit on process automation. I shared earlier that it's a high priority for mid-sized to smaller size operators, and really for many operators. But in this particular case, again, we had properties in mass. So there were a lot of properties that needed to be evaluated. And in this case, they had a machine learning model to be able to predict production for each one of these wells. However, the prediction of this machine learning model had plateaued, meaning it didn't really reflect any improvement in productivity, especially as you moved away from your core data set, right? And of course, we are always taking on the diverse data sources problem. So the challenge was to improve predictions of well performance, meaning bring that predictivity from that existing machine learning model up through potentially understanding what is the machine learning model needed. You have a current data set and you're obviously missing something because the predictive model is not able to get better, right? So the idea here is to actually use some of the high detail level, high resolution 3D modeling of the subsurface and gain insights from that to be able to elevate the productivity of the machine learning model. So again, it's trying to couple those workflows to be able to extract more value. There was a prediction improvement noted after this was done through the actual understanding of what the physics of the problem was represented in the 3D numerical model. So let me explain a bit more on what I mean by saying a 3D numerical model. A reservoir simulation at a glance. Reservoir simulation in the oil and gas industry is just really a couple nonlinear, a software that helps solve nonlinear partial differential equations that describe the fluid flow through the rock. It's basically a solution to these partial differential equations that are found numerically. So for a change in pressure, I'm going to see a representative volume, right? Or vice versa. So it's just trying to understand these differential equations that dictate the fluid flow through their system. It is time and effort intensive. It requires a lot of data and expertise. But the idea is that that representation of the rock, you're going to build a computerized model for that representation, and then you're going to run time scenarios. So, for example, if this is my reservoir and this is my subsurface, I'm going to run a representation of this specific segment of rock. In this case, it's about 2 miles or about 3 kilometers wide and about a mile high. And you can do that and represent it pretty well in a computerized model. You can see here the faults are represented. And then from there, you can actually start running what if scenarios. What if I drill a well here? Well, then you will get a certain production behavior based on certain conditions. And the computer can do that because it can solve those partial differential equations. But then the challenge comes when you have to do another iteration at another area of the field. What if you actually want to drill here? Then you have to start all over again, right? And that's where it becomes really, really time intensive. You can, and for the unconventional system, which is very predominant here in the US, it really becomes a tall order to say that we're going to be able to model in a 3D numerical model like this every single well we have, because we're talking about thousands of wells. So it really becomes a tall order to do that. So how can we actually leverage some of these insights from this software, for example, and embed them in something that is faster, like a machine learning model? Well, that's where this is really handy. This can help, for example, if you were to use existing open source code to help optimize some of these existing workflows in the numerical reservoir simulation world. It can help you generate a template-based model. So if you're familiar with Python and Python coding, you will recognize the term of cookie cutter, right? So it can help you cookie cutter just skeleton scenarios of what that reservoir model could be. You can apply continuous integration and continuous deployment techniques to actually be able to categorize every iteration that you have. And then from that, you can use workflow managers like Luigi and Django to actually be able to extract the insights of each one of these runs and store them appropriately so you can learn from them and gain insights when you apply this workflow and run reservoir simulation models in mass. By doing this in mass, you are able to actually understand what the response of the partial differential equation is based on multiple conditions. So this is just a simplified example of the template that I'm talking about. This will be your cookie cutter template that Python will generate for you. And then from here, you can store it and run this workflow semi-automatically using open source tools. By having this template, you can actually run different sensitivities across your entire parameter space. So you capture those iterations from the response from the simulator, you store them, and then you rapidly vet them for input data to be used in a workflow like machine learning, for example. One of the big challenges that you can encounter doing something like this is the different variations in data. So data cleaning and cataloging from multiple messy data files can be a challenge. Uh, After applying this workflow, you're more than likely going to get a series of files or output files from the simulator predicting the production response. So in this case, for example, you can see that there is a date, an oil rate, a water rate, a gas rate. Those are the predictions from the partial differential equations that were solved, right? This is just one case and one scenario. When you're running them in mass, you're going to get many different ones. So you have all the outputs and you have all the inputs, and they can be messy even in these structures, right? Because they don't come all with the same format. You can see some are, different strings, different outputs, different text files. So it can be a really messy task to be able to catalog what you really want from each one of these files and store them in a way that a machine learning model can then use it. So that's, again, when process automation can be very helpful. Because if you were to use, say, for example, Luigi tasks to automate data cleaning steps before cataloging what you really want in a database, you can actually help alleviate some of this manual data burden that sometimes can come in when you're running this type of workflow. So you're saving time and efficiencies in two ways. You're saving time by actually optimizing the way you run the simulator, and you're saving time by the way that you're grabbing the simulator outputs and storing them in a format that it can be readily used for another workflow, like, for example, a statistics-based approach. This was it's been very useful, and it's basically using Python as a glue to help you maximize resources and gain effectiveness in your existing workflows. The idea of doing this is also very appealing because it can help you store and catalog data that is not just used for one workflow. In this case, we're talking about reservoir simulation, but in many other workflows like statistics-based approach and the other workflows that I was sharing before with you, like the that are more on a higher resolution level. So then it comes about decisions, right? How are we going to be able to choose the appropriate schema to store all this data? So you have optimized your reservoir simulation modeling exercise by semi-automating some of the work. You have also optimized how you grab the data from the simulator and how you catalog it. But now, how exactly are we going to catalog it? And then you have a whole bunch of different options, right? This is a data talk, so we're gonna talk about some of these decisions that have to be made. Normally, this workflow that I'm sharing with you is done as a proof of concept, right? Can we actually gain efficiencies? Can we actually maximize the resources by applying the traditional engineering workflows and basically adding more efficiency to data science or that other analytic techniques? So you have a lot of different options, as we know, from the most simple of the options, the star schema, all the way to all the more complex data warehousing options. The key to understand is the project scope, right? What I'm sharing is this is a proof of concept, so we have to keep that in mind. We also understand that this is a multidisciplinary data components. I was sharing with you earlier that simulator takes geological data, engineering data, data from multiple sources. So with that, what are our choices? Let's start with the most simple of the choices, the star schema. This is very useful sometimes when you have these multidisciplinary data components because you can add them by discipline, for example. Each star is going to be a different discipline, and the querying is not as complex, right? Because you have them by each of the disciplines that actually contributed to the data in the workflow. On the other hand, you have a bit more complex structures that you can leverage. If, for example, you have to keep track of the wells, each well ID, each run. So you can do something like a snowflake schema, right? It's a little bit more intensive when it comes to querying, but you are going to be able to link things that you couldn't before or you didn't have access to before. The other options, of course, it can get more complex. You can get to a galaxy schema where you have multiple star schemas linked together and with shared properties as part of their union, right? All of this can be in consideration as where do you want to go next. Now, the good news is that you don't have to make the decision right away on a proof of concept. The idea is to keep the proof of concept simple. So in this case, you have proven the concept that you can gain value from traditional reservoir simulation workflows by enhancing them with data science techniques. And now the idea is to store this and provide value by keeping it simple. So sometimes maybe just a star schema will do. Now, what is the result? Remember, I was sharing with you that we were having the machine learning model that we had was in this world. In this model, model explainability was very important, right? Trying to explain the outcome of the prediction was linked to a variable that we could control. That was very important. But be able to actually understand that extra piece of the physics that we didn't have before through the simulation exercise, we can actually help elevate some of the predictivity of the workflow, not just by adding more robust machine learning models, but by adding more information that we didn't have before from the physics-based approach. As I was mentioning earlier, the physics-based approach, what it does is just shows you what the physics of the system as we understand it, how is that represented in a partial differential equation or a system of a partial differential equations. And the response from those runs are being captured and stored and cataloged in a way that can be used in a machine learning model. With that extra inside of information, that machine learning model can actually become more robust and without really losing a lot of its explainability. Now, some of it could be lost depending on what machine learning model you want to do. But this is where these two actually have some level of synergies that can be leveraged. The other benefit as well is that statistics can help understand at a high level what are some of the potential pitfalls of the data that we have. If you look at a well at a localized level, you can really pretty much match the behavior with any set of parameters because it's a very non-unique answer in this reservoir simulation world. When you look at the data at a holistic level, at a field level, there are things that are not really going to match or jive because they're going to have to be make a lot of big extrapolations to be able to fit the field-wide performance. So that's when these two techniques actually can help each other. One can add insights from the actual physics of the problem, and the other can help QC and vet data, and vice versa. So by elevating and leveraging these two, you can actually understand and get more value from existing workflows. So the key is the integration of viewpoints, tools, and workflows. As I was mentioning, in the oil and gas, upstream oil and gas, we have diverse data from many different disciplines: reservoir, geology, production, asset management, completions. All of them, they have a piece of the information, a piece of the pie. The idea is to put them together in a cohesive story. And for that, we have several tools at our disposal, right? We have the traditional tools that help us do that. And some of these are, for example, the different reservoir simulators that we were talking about. There are the other tools that we were looking at before that are more on the higher resolution well by well level evaluations. They help us understand the productivity of each one of the wells. And they help us understand what were the main variables that helped enhance that productivity or hinder that productivity, depending on the case. So the idea is to get the understanding from these tools, but also get them faster and more efficient by leveraging open source tools that can help make these workflows a lot more effective in areas, for example, like unconventional reservoirs in onshore use. Those are areas where we have a lot of wells, a lot of data, and we don't really have the luxury of time to go through each one of them and do the evaluation using every single one of these traditional engineering workflows. So for that, the case study that I just shared with you helps us leverage open source tools to maximize value from existing software and engineering workflows by also leveraging the data that comes from multiple disciplines and multiple sources. The implementation that I share with you, some of the learnings is, of course, keep it simple and scale up for value. So start with identifying where can you process automation really help? Where can you really add value by either reducing the amount of time that is being spent in that workflow or by helping on add more understanding of the workflow by including different data sources and different types of analysis that hasn't been done before. So identifying those high value use cases is quite important because then you can prioritize according to value and the feasibility of the project that you're about to embark on. And of course, focusing on the ones that have the most likely chance of succeeding. Once you develop that, you are tasked to develop a proof of concept. And that's, keeping it simple is critical because then the idea of that proof of concept is to prove potential. Can this actually work? It may be in a smaller subset of data or in a smaller field. Once that is done, it's about building a minimal viable product or actually an end-to-end solution for that that actually elevates that proof of concept. For our work, we said keep it simple, data structure, data management simple, because as you build your minimum viable product, you're going to be able to expand on that. And this is where it takes a bit of all these steps are going to help you with managing change. And of course, scale up on basis of value and terminate initiatives that could fail to add value and terminate them quickly. The idea is to build a flexible workflow with a flexible data infrastructure that will add value and help you change management along the way. When I say change management, it's basically change the way people traditionally do their work. Um, so key takeaways, data is in the wild is wild. So there is the need for using integration of diverse methods to be able to add or extract more value. Keeping it simple and scaling it for value is key to be able to demonstrate that the workflow is actually going to be able to help in what you're doing day to day. The synergy of multiple approaches can really unlock potential of complex systems optimization. And of course, teamwork is essential. Change management takes effort to be able to do that. So these steps and doing it, accordingly can help with that change management approach. So thank you very much. Appreciate your time. I'm happy to take any questions.
Okay, there's already one question from Nelly. Which element of this funnel would you say is the most difficult to implement in the industry today?
Awesome. Thank you, Nelly. So let me go. I'm thinking you're talking about the funnel that we saw a few slides back. We have to go back a few slides. It's this funnel, right? So, I recently read an article which is really interesting, and I think it hits on all the marks. And it's about 50% of the effort is change management on all of these approaches. So, my opinion, I don't necessarily think it's a technical. We don't have. It's not like we don't have the technical resources. It's about trying to change how we the paradigm shift on how we normally do business to a different way of doing business that sometimes can take effort and also cost incentives. Whatever is most cost effective or whatever is more timely, it's normally what we tend to lean towards. And a lot of these processes, they take time and significant resources to implement. And that's why it's really important, in my opinion, to show value quickly. So more succinctly, I think change management is one of the things that is really a common denominator that is requires significant time and attention to be able to change for any of these funnel elements. Thank you for your question.
And Norman says, could you please redisplay the takeaway slide?
Sure, let's go all the way back. This could be a lot easier, but just do this. Here we go. So the takeaway slide.
Any other
Thank
questions?
you for
Yeah.
yeah, thank you for your interest. I'm happy to take any questions offline. And I don't know, are we sharing our information?
Uh, like how people can reach out to you?
Yeah.
Yeah, of course.
Awesome. So yeah, let me do that. I think I'm happy to answer any additional questions here. Can be reached at. Thank you. Thank you so much for your time, and
Yeah,
I
I think
hope.
presentation was great. Like it was mixed of science and engineering at the same time, which was good.
Thank you. Well, I'm really happy to hear that. I'm happy to answer any more questions and just discuss of specific situations you have in mind. So thank you for the opportunity.
Okay, then question is coming from me. So,
Sure.
is there any kind of possibility that you can build platform specifically for data to ML for the uh, oil business? What do you think about it? Like, uh, so for example, in the Seguin, are you building more like a ML platform that you can do stuff end to end from UI?
Yeah. So I think ML, yeah, right. Everybody seems, we're all excited about ML and it's great. It's like the cherry on top. But really, where we tend to spend, or I tend to spend most of my time, is on the other stuff that is underneath it. When we were talking about the different data schemas and data infrastructures and how to set them up so that it actually can capture the value from the other workflows so that we can get to that point where we can deploy them in a statistics based approach or a machine learning model. That's where most of the work happens. And yes, a lot. That's really a lot of where the time and investment is right now in oil and gas as well. Is trying to understand that data infrastructure that will get us to where we need to go. We still have struggles, like for example, we have vintage data sources, wells
Hmm.
that have been drilled in the 50s and 60s. They didn't have like digital data infrastructures, right? We are still talking about those paper files that they were using in that. So it's just trying to understand what can we bring up to date, how to bring it up to date, and just even things like what are the common keys to use. One
Hmm.
discipline might say pressure, and it might mean something different to another discipline because we have pressure at different points across the cycle of the well.
Yeah.
So that is something that is really critical for us, is just to what is a cohesive way to put these data sources in a structure and in a theme that actually can add value, joining different disciplines in multiple points of view. So yeah, to answer your question succinctly, that's kind of what we want and we're working and we have before we even do machine learning, but we're still progressing it. We're not, in general sense, I don't think we have gotten to a point where we have a data infrastructure that is really leveraging all the data that we currently have at hand.
Hmm. Yeah.
Thank you for your question. I think it's also a fair theme across many different industries that have been around for a while, right? Like the oil and gas industry has been around for a little while. So when it comes to digitalization, we have this task of trying to blend or bring up to all this new modern data infrastructure system, um, data that was captured many years ago, and get value from that. So in some sense, we're focusing on the more recent data because we're getting bombarded with that a lot. That's where our focus is.
Hmm.
But in another sense, eventually we're going to have to put a lot of time and effort into the other data sources because those wells, you know, we need to extract more value from those wells as well. So there have been operators that have been very successful doing that, just extracting value from late life fields, which basically means trying to understand that vintage data and bring that vintage data to be able to coexist and be able to be utilized in more um, modern workflows.
Mhm. Any other questions, guys? So there's actually one question in the Q&A.
Yeah.
So congrats for the presentation. In what ways do domain experts in the oil and gas industry, in this case, evaluate the effectiveness and reliability of machine learning algorithms compared to traditional methods?
Yeah, very good question. So they are not necessarily comparing apples to apples in many ways, and normally the proof is in the predictivity. If some of these methods are really effective for looking back and trying to diagnose what happened to the well. Why did the well go down? How to remediate it? How to do those things? So they really look for understanding that. But for example, the reliability of machine learning is normally put to the test through the prediction, right? Does it predict the behavior? Is it telling me that when I drill this well, I'm going to get X amount of barrels, and I actually get X amount of barrels? Then there is more buy-in on that machine learning model. That's why they kind of work together, right? A set of tools can help you understand, oh, why did this well didn't come or lost production, or it's more of a diagnostics, more of a really trying to understand or investigate what are the underlying causes for the missing production or the outstanding production that you probably got as an outlier, right? Now, the idea on how to benchmark and how to evaluate the effectiveness of these tools is normally boils down to the prediction. In the sense, and also boils down to much how are they applicable to a specific problem. Not every single tool is going to be applicable to the same problem. So it's trying to understand and that subject matter expertise of the tools and the workflows and the problem at hand to be able to say, yes, this tool is effective for this problem. Like I shared with you before, right? Like reservoir simulation in the context of thousands of wells. Well, it's probably not going to be a very effective tool for every single well. But there are things that you can do from it, or you can glean from that you can use in a more effective workflow that can handle statistical significant data sets like thousands of wells. So the idea is to complement those learnings, knowing the limitations of each tool.
Yeah.
Thank you for your question.
Okay, then I think that's it.
Okay, well, thank you very much. Appreciate it. Very nice chatting with you today.
Yeah, it was awesome. So have a good one. Bye.
You too.